Swayam Prabha. Digital India. Educated India.
Good morning, everyone. So, we'll continue our discussion on power amplifiers in millimeter wave systems now, right? We have figured out the other building blocks that we need in the transmitter, for example, right? So, we'll focus on the power amplifiers. I'll review the class A design of a power amplifier again, just to make sure that we are starting from a common point, right? The general idea is that we have, let's say, a common source device, right? And we, for simplicity, I'll call this an L choke. It can be incorporated as part of your other networks if necessary. And imagine that over here you have a very large capacitance, C large, right? And then we have a resonator that is tuned to F0. Right? And then we have our load connected here, which is RL, and this is VDD, right? So, in order to extract as much power as we can out of this PA, what we would like to do is, of course, get power into the load, and we can define the current that is flowing here as I0, right? And the current that is flowing through the load as IL, right? So, we know that the power that will be delivered in the load is IL squared RL divided by 2, right? So, where IL is effectively the amplitude of the sinusoid at F0, right? This is what IL is referring to, the amplitude of the sinusoid. We see that in this system, the fundamental current will flow over here. All the harmonic currents will end up being shorted out by the resonator, right? And the DC current will flow over here. So, no DC current flows through the capacitor, of course, right? And then we have the current that is there in the transistor. So, if we think of the current in the transistor, that is going to be equal to IDS plus I0, right? And if I think about the voltage across a transistor, right? So, you can think that this capacitor will be charged to VDD at DC, right? Because no current is flowing through at DC. And so, any voltage that is at this node, you have to add the voltage across the capacitor to get to this node. So, then we can say that VDS is going to be equal to VDD plus IL times RL, because that will be the current. So, if we decide that this current is IL sine omega naught t, right, then we can basically say that this voltage VDS will be ILRL sine omega naught t, right. So, if we were to now start plotting the current and voltage for the transistor, right. So, let's say that I am biasing it at a certain IDC, right. So, if I were to plot the current in the transistor, right, this is IDC, right, and then as IL swings up and down, that current flows through the transistor. Let's assume that we're operating in the linear region and no harmonics are present. Then we'll basically get a current that looks like this, right? And this will happen at the time where, if I were to think of the voltage, it is going to look, VDS is going to look like this, right? So, what we end up, and for VDS, this is going to be VDD, right? The midpoint is going to be VDD. So, if I look at this node voltage, it is going to swing up and down about VDD, and my objective is to make sure that I extract as much power as I can. So, I would like the swing magnitude to be equal to VDD, right? And since I want the swing magnitude to be VDD, and I want to make sure that even the current is swinging as much as possible, I can make sure that happens by applying the equation that VDD is IL times RL, right? IDC times RL. Because if VDD is IDC times RL, then when the current swings to the lowest, I will get the maximum swing that I can get on the device. So, this is the point of getting maximum power out of the PA, right? So, then if I look at my PDC that I am dissipating, right, this is the only source of DC current. So, that is just VDD times IDC, right? And then if I think about the power that I am dissipating in my load, I am getting IL squared times RL divided by 2, which is IL squared, the magnitude of it is also IDC, right? So, this is IDC squared divided by 2, but RL is VDD divided by IDC, right? So, this basically becomes IDC times VDD divided by 2. So, if I think about the efficiency as PL divided by PDC, I see that I am operating at 50%, right? So, a class A amplifier, if you apply, now in order to make sure that there is a certain IDC, I have to bias this amplifier. So, I can think of my Vin as some RF signal magnitude, right, plus some V bias, right, where I am basically making sure that that V bias supports the IDC through the transistor, right. So, the idea becomes that you pick your transistor, you pick the bias that sets the IDC, right, and then you can design. Obviously, for the same reason of trying to operate at the best efficiency possible, right, you want to make sure that the IDC that you pick is appropriate for the RL that you have, right. So, you can pick the IDC with this equation. This is similar to what we call load line analysis, right, and to the first order tells you how to design the load. This isn't completely what we can do in practice, right, but to the first order it tells you how to design the load. Now, we also see, of course, that the power that is dissipated in the load, right, at most is going to be, I'm just rewriting this equation another way, but basically it's going to be VDD squared divided by 2RL. So, if I'm limited in my VDD, then I have to decrease RL if I want to increase my PL, right. And if I do that, we saw that there was a network efficiency factor that we had to live with, transformation network efficiency factor that we had to live with, and we will discuss that some more, right. So, the observation here is that in this particular design, I assumed that everything was linear. So, there was really no current even flowing through the resonator. So, I could just have eliminated the resonator and built a class A design. But I see that I can take advantage of this resonator and live with some more harmonics in my IDS, and then have them filter out, right, and see if that improves my efficiency. So we consider this design which we call class B, right, and let's again consider this device, right, and again we'll bias it with a L choke, right. In subsequent things we will see how to absorb all of this into our network itself, right, but right. So the idea in class B design is that I bias this device, right, I am biasing it at 3, so this is V in, let's say sine omega naught t plus B threshold, right. So let's plot the input waveform across time, right. So if I consider the V gate or VGS, right. So VGS, the DC value is VTH, right. So the DC value is VTH. So let's consider a scenario where the input swings like so, right. Right. So we have an input swing that is like this, but this is VTH, right. So what is happening is that the transistor is on only during this part of the cycle, and at this part of the cycle the VGS is below the threshold, so the transistor is not pulling any current, right. So if I were to then plot IDS, I'll just sort of extend this axis below and so that we can see what is happening, right. So what is going to happen is that the current through the transistor is going to look like a half sinusoid, right. It will be 0 here, and then again in the next cycle I am going to get something that goes like this. Yeah. No, the voltage and the input voltage and current will be in phase, right. The input voltage and current are going to be in phase. When this voltage goes up, this current goes up, right. So, but now clearly this is not a, this is not a sinusoid. It has a DC value, right. It has and I can split this into Fourier components of IDC, let's say I fundamental, I second harmonic, so on and so forth, right. I can represent it as a sum of harmonics, but now what is interesting is that this over here is IDS, right, but this still the choke is not going to allow any current to flow other than the DC current. So only the DC current is going to flow through the choke, right. And you can show that if this magnitude is IRF, okay, then what we can show is IDC is IRF over pi. If you average this over cycles, you get IDC as IRF over pi, right. So now that DC current is going to flow through this choke. What is left is going to be flowing this way, right. So you are going to get, if I call this current now I naught, right. So I naught plus IDC is going to be equal to IDS. So I naught is just IDS minus the IDC that is flowing through the choke, right. Now if I subtract the average out of this, you can clearly see that this will just be an offset waveform, right. But even that is not a sinusoid. So it has many harmonic components, but all those harmonic components will get shunted out here, right. And then what I will be left is my IL, right. will only be the fundamental part of IDS, right? And for this waveform, I can show that the I fundamental, right, is going to be IRF divided by 2. That's going to be the magnitude of my fundamental. I don't care about all the other currents right now because I just know that they're going to get shunted into this. So they're not going to create any voltage at this node. So the voltage at this node BL, right, is just going to be minus IL RL, right, which basically even in the class A this should have been minus and I should have tracked it, but that's okay. So then we basically see that BDS, right, is going to be the same situation, that this capacitor gets charged up to VDD. So you get VDD minus IL RL, right? But IL RL is a fundamental component, right? So if I were to plot IL, right? So I'm now plotting IL, let's say in red, right? And IL is going to be a sinusoid, right, at the fundamental, and this magnitude is going to be IRF divided by 2, right. And what this is saying is that the output BDS is VDD minus ILRL, right. So I'm going to end up with something which, if I were to extend this even further, right, I'm going to end up with something where if I look at my output waveform across T, let's say that this is VDD. So this is VDS that I'm plotting now. So this node will be VDD and this will be, as you asked, out of phase, right? And this is going to go up and come down like this, right? So even though my IDS is not a pure sinusoid, my VDS and my VL are pure sinusoids. Is that okay? Sorry? VDS and VL are both pure sinusoids. IDS is not a sinusoid, but that's okay, right? Because I'm shunting all the harmonic currents into this filter. So now, again, it is my desire that in order to extract maximum power, I swing as much as possible, right? So I need to make sure that this swing is VDD, right? So now, but this swing is basically, it's going to be IRF divided by 2 times RL should be equal to VDD, right? So this basically says that in this particular case, I should make my RL 2 VDD divided by IRF, right? Where IRF is the peak IDS, right? It's the max IDS that is happening in the class B design, right? And now that I have done this, I can find out in this optimal scenario, right, for max swing, right? So in this optimal scenario, then I know that my fundamental is IRF divided by 2. I know my DC is IRF divided by pi, right? And I know what the optimum load resistance that I need. So now I can basically find my P out over PDC, right? Or PL over PDC, that's what we've been using. So if I think about PL is going to be nothing but just, so we are going to swing a whole VDD across the load. So the PL max that I'm going to get is VDD squared divided by 2RL, right? That's the maximum that I can get, right? And what I can basically show is that my efficiency at the maximum point then, or the maximum efficiency is going to be PL max divided by PDC, and that is going to be equal to pi over 4 or 78, approximately 78% efficiency. right? So the class B PA is more efficient than the class A PA. It is clearly non-linear, but I'm relying on my filters to shunt out the non-linearities so that I still have a linear relationship between input and the output that is being dissipated into the RL, right? But as long as I can make good filters like this is going to give me improved efficiency. Does it make sense? So we can now extend this idea still further or less. Both options are possible, right? So we can either operate in what we would call class AB, where this V bias that we are applying, right? For in class A, we are applying a V bias that is well above threshold, right? Then class B, we are applying a V bias that is equal to V threshold. Class C, we can apply a V bias that is below V threshold, right? In all cases, or we can also operate in class AB, right, where the V bias is V bias is high that there is still some default DC current going through the device, but it is not so high that you don't have this kind of phenomena, right? So I can think about a situation where I'll just draw the input VGS and IDS. So I have my VGS. So this is V bias, and my VGS is going to swing up and down over it, right? And depending upon where this V bias is with respect to the threshold voltage, right, I can have my IDS, right? I can have my IDS either, so class B, it will be on for full half of the cycle, this is class B, right? Or if I think about it, so, and if I think about class C, it's going to be on for a smaller part of the cycle because, right? So this is class C, right, where V bias is less than V threshold, right? So the IDS is on for less than the cycle. Or I might have a situation where I do class AB, right, which I will show here, but there will be some DC current, right? So in that case, let's do this in red. What you will see is that it runs for more than half the cycle, but then zeroes out and then runs for some more part of the cycle, right? So this would be class AB. In all cases, right, the IDS contains both fundamental and harmonic components and a DC component, of course, right? But the job of this filter is to take out the harmonic components, leaving only the fundamental to go through, right? So from the perspective of looking from here to here, you are linear from input to output, right? And what is intuitively you can see here that when we have class B, class C or even class AB design, the DC current increases in proportion to this amplitude, right? Since the DC current increases in proportion to this peak current, we basically have some scaling of power that is happening. The DC power scales with the output power to some extent, right? That's a class B design. In a class A design, whether you apply the signal or not, the DC power is going to stay the same, right? Because it's just VDD IDC. But in a class B design, if you don't apply any signal, the transistor never turns on. So that's zero DC power consumption. Only when you apply the signal does the transistor turn on. So there is some scaling of power, right? So class AB, class C, B, class C, right? All of them, right? DC power scales with input and hence output power, right? Which is a useful thing from a power amplifier perspective. What we can also see is that just like from moving from class A to class B, right? We moved in efficiency, peak efficiency from 50% to 78%. In class C, if you go to a zero conduction angle, you can go all the way to 100%, right? But then at that point, you're delivering infinitesimally small power as well, right? So class C lets you get even higher efficiency, but you can also see that it has more harmonic components. So the job of this filter becomes more and more important as you reduce what we call this the conduction angle, right? So we call this the part of the cycle that it is on for, we call this the conduction angle, right? So as we reduce the conduction angle, right? So we have a formal definition for this where class B is theta is 180 degrees, right? And class C over here, theta is less than 180 degrees, right? So depending upon how low your conduction angle is, your harmonic currents are going to keep increasing. And this is going to be a problem because it stresses the filter to remove these harmonics in the design. But it gives you efficiency. So this is the basic classes of operation. We will not discuss other classes of operation in this, both due to a limited time, but also the fact that these other classes are not that prevalent in commercial millimeter wave PA design. There is a lot of research PA design where people have demonstrated class E, class F amplifiers at millimeter wave. In all of those cases, basically what you're trying to do is harmonic shaping. You're trying to, from a system level, create an objective, because what we see over here is that the I peaks when the VDS goes low and the I goes low when the VDS goes high, right? So if I think about it as power dissipated in the transistor, this is a good scenario, but the best case scenario for me would be a situation where if I could make a plot where the IDS looked like this, right? And the VDS looked like this, right? So basically, one or the other is always 0. So so this is IDS, comma VDS, right, across T. And now, of course, if I am able to, even this will work. I mean, I don't need both to be square waves. This could be a sinusoid, for example, right? The voltage could be a half sinusoid as long as the IDS goes to 0 when the VDS goes high. So I can do harmonic shaping through many different ways to try to create these kinds of waveforms so that I am reducing the power dissipated in my transistor, right? I am reducing that, and then that my overall DC power is the power dissipated in the load and the power dissipated in the transistor, right? So if I'm able to bring this down, my efficiency, which is my P load divided by PDC, increases, right? Now, this equation is a little incorrect, right? Because these are not the only things that I'm applying in. I'm also applying technically a P in into my system that is driving my amplifier, right? So this efficiency doesn't capture the whole metric, right? So we call this then the drain efficiency. and we have a term that we call the power added efficiency, or the PAE, right, which is P out minus P in divided by PDC, right. So, in this let us say that the PA has a certain gain. So, this can be written as P out divided by PDC times 1 minus P in over P out. So, this is basically P out or let's this is drain efficiency times 1 minus 1 over G, right. So, this starts impacting your design. So, that is statement 1, right. Statement 2 is that in all the class A, AB, B, C designs, etc., I assume that when I have the transistor over here, right, and I am considering this this node, the swing on this node. So, this sets to VDD, and this node over here is swinging. If I rotate this, my claim is that this node goes about VDD. So, it swings let us say up and down, right. And I assume that I could have this keep on increasing until it was able to hit VDD, right. In practice that does not happen. So, in practice there is a minimum voltage that you can go to. So, that is V knee, right. So, then basically my swings become limited to VDD minus V knee, right, divided by, so in all those equations, for example, where I write I try to find out what the maximum, what the best case RL is, I have to replace 2 VDD by 2 VDD minus V knee, right. So, in the simple class A design, we can simply say that where we did VDD is IDC RL, we just say VDD minus V knee divided by IDC is RL, right. And what this effectively means is that your maximum output power, right, is less than VDD squared divided by 2 RL, right. It is now actually VDD minus V knee squared divided by 2 RL, right. That is the maximum output power in the class A design, right. But your PDC is still VDD times IDC, right. So, what you find is that your efficiency becomes less than the theoretical 50% because of this existence of this knee voltage, and this happens in both class A, class B, or any linear PA design. And why is this significant? Well, if you lived in a world where your VDD was 2 volts and your V knee is 100 millivolts as an example, then this delta is negligible. But if you are operating with a VDD of 0.8 volts and the V knee voltage is still 0.1 volts, this is basically 12.5% of your swing. So, it is going to really impact your efficiency and bring your PA efficiency down, and that is what happens at millimeter wave, right. So, this knee voltage is a problem. So, given, so this was sort of the first order way to find out what RL we have, right. But in reality what we have is a situation where when I have a device, right, this device also has, if I look this way, it also has some parasitic capacitance at the output, right. let's call that C naught, right? And so when I am trying to figure out what is the best load that needs to be presented here, right? What I end up finding is that if all of my assumptions were based on the fact that all the current went through this capacitor and then went out into my load, right? But now some current is going to start getting shunted here. So then I see that the optimum impedance that I need to present here in order to get as much power as possible is not quite BDD over IDC. It's not just the RL. And so I can, in order to find out what it is, I can decide that I'm going to make my load RL plus J itself, right? And I'm going to sweep RL and I'm going to sweep J itself, right? I'm going to sweep it through all possible values. So RL can be swept from 0 to infinity. J itself can be swept from minus infinity to infinity, right? And then I will keep looking at how much power is dissipated in the load, and I will get an optimum impedance that will give me the best output power. Now, when I'm running that analysis, it matters what input swing I provide here, right? Because if I provide too small an input swing, it will give me an answer, and if I provide a very large input swing, it will give me a different answer. So there are two reasons for this. One, of course, that as I am providing a larger input swing and this is swinging up and down, that's a more realistic estimate of what the maximum output power is. Because I'm then hitting my V knee and going up to the 2 VDD limit, right? But there is also the other part, which is that all of these capacitances over here, in particular Cin also is a variable capacitance, and because the gain from here to here during different parts of your swing are different, right? When your swing is about 0, depending on your bias, you have a lot of gain. When the swing goes low or high, your gain changes, right? So in that scenario, the CGD capacitance that you have is getting modulated by a different gain. So you have this Miller effect here, right? So as a result of this, when I look in from here, I start seeing nonlinear capacitances in my system, right? And of course, everything about my model, right? This, if we consider the small signal model, the GM, right? The C out, right? All of these are varying throughout the cycle, right? So in given all these nonlinearities, I do like a brute force search to find out what this RL plus J itself is, right? And what I can see is one way to represent searching through the entire space is to say that I will search at all points on the Smith chart, right? Where I'm representing the load, right, in terms of its reflection coefficient. So ZL minus Z naught divided by ZL plus Z naught, right? This is gamma L. And you can show that when you vary the load across this entire space, you are basically varying it inside the radius of absolute value of gamma equal to 1, right? So inside this radius, you're putting all the reflection coefficients. And what we typically end up seeing is that the transistor wants to see something that is in this region, right? And you can plot circles of impedance, and there is a logical reason for it, considering constant impedance lines and constant reactance lines on the Smith chart, right? There's a logical reason for it, we can derive it. But effectively, what you start seeing is impedance output power circles, where what this is saying is that this point here, if I'm able to present this load, then I get the best output power that I can get, right? And I can optimize either the OP1 dB, right? So I am assuming that there is familiarity with the OP1 dB metric, but basically just to quickly review that, as I am applying a small voltage input or small Pin, right? I expect my P out to increase linearly because my gain is linear. But what might happen is that, or rather what will happen is that my P out will start getting what we call compressed, right, because of the nonlinearities. And there'll be some point where it will be 1 dB below what it's supposed to be, right? And this is a metric that we consider of nonlinearity, right? So this point over here, right, is what we would call the OP1 dB or output referred 1 dB. So you can do these circles for OP1 dB. You can do these circles for what we call the maximum power that it's going to generate, which is P sat, or the saturated output power, right? That beyond a certain point, all this compression just made sure that you cannot generate any power. Or you can create these circles for efficiency, right? So when you perform load pull, this act of applying many different loads and seeing what power and efficiency and OP1 dB that you get is called load pull, right? It's a brute force way of doing the load line, right? But it basically takes into account all the non-idealities in the system. So we can do it to either optimize power added efficiency or OP1 dB or P sat, depending upon our system metrics, right? Starting with P sat is a useful metric because you just provide enough input signal swing to make sure that your device is going to be in this region, right? So whether you are a little bit below or above doesn't matter. And once you get a sense of what the P sat optimum looks like, then around that region you can do a load pull to find out which is the best OP1 dB load or which is the best power added efficiency load, right? That's typically the design practice. So let's say that at the end of it, we got a certain Z opt, whichever metric that we ended up with, we got a certain Z opt. But the intuition of the load line, which is that the PDC is VDD squared divided by RL, that intuition stays. So you can see that basically if I consider this point on the Smith chart, it is going to be something where the real part is going to be quite small, right, or smaller than 50 ohms, right? So usually then what I have to design is that I have my transistor, and again so far we still have the choke, right? And then I have this capacitance over here. And now I basically have to design a transformation network that moves my Z naught, right, typically 50 ohms, right, because the PA typically is driving the antenna. And what the objective is that you want over here in this plane to see Z opt, right? So this kind of transformation network, we looked into wideband transformation networks. So quite often it is useful to have both wide bandwidth and impedance transformation, right? You might want to go from 50 ohms down to 25 ohms, for example, right? So we saw the design equations to do that both from a simple series stub matching and also from a higher order resonator approach, right? And if we use the simple shunt series sort of matching, the efficiency of our matching network is QU divided by QU plus QN, right? Where this QN depends upon RL over the real part, let's say, of the R opt that we want minus 1, right? So then this, if I try to do a very large transformation, then I can see that QN is going to be large, right? If I try to do this with the fourth order resonator, and we discussed this briefly in the tutorial yesterday, but with the transformer approach, right, it's -1 plus square root of 1 plus kq squared, right, where the q is defined as square root of q1 and q2, right, where these were the q's at the two resonance frequencies that we defined yesterday. So this divided by kq square, right. So what this is basically saying is that in this case, in order to get good efficiency, right, you want to have a good kq product, right, which basically means that if you are coupling with small k, then you need to use very good quality factor inductors, or if given a certain quality factor inductor, then you can get a certain insertion loss by picking a high enough k to build the system. Let's say that I'm transferring this 50 ohm. My objective was to make this look like Z opt, right? But in the small signal, what I see is this doesn't look like Z opt, right? This is not equal to Z opt. So if this is not equal to Z opt, just the reciprocity of the network, this over here will not be equal to 50. Since this is not equal to 50, it will not be matched to 50. If 50 transforms to Z opt, something that is not Z opt is not going to transform to 50. Yeah. So this basically means that S22 will be poor. Right? Is that it? So the task of PA design then becomes that once you get a device, right, you take that device and then you perform load pull on it, you find the optimum load you want to see, then you design a network to transform it, right. What about the swings itself? We apply VDD here. So we know that we expect over here the swing to go, the voltage to go up to 2 VDD. That typically happens when the input voltage goes low, right, because these two are out of phase with respect to each other. So you are effectively getting a voltage that is here, which is approximately 2 VDD, right, and that's typically sort of near breakdown voltages or near reliability swings for the technology, right. So the technology can tolerate 2 VDD between drain and gate usually. So that's what basically sets the VDD. So you don't have the option to really increase the VDD too much, because if you increase the VDD, then you are creating a worst case drain gate swing that is much larger, right. One way to address this, of course, is to say that you'll build the PA as a cascade. And then this node voltage is VDD on the cascade, right? So, or let's say, I mean, just to, yeah. So then you can, design this with a larger swing, because you can accommodate some larger voltage here, because this swing over here, right? You may be able to tolerate a larger drain gate voltage swing, and this node over here is not going to swing all the way up and down to VDD, right? So you still have the option to, so Vn goes like this node voltage goes like this, right? So in the high point to the low point, it is not going to be 2 VDD, so you can get higher output power by building a cascade. In that case, you start getting limited by this over here, right? There are diodes here, right? So what you start getting limited by is the breakdown voltages of these diodes at the drain. The drain to bulk diode breakdown is basically what starts limiting you. So you can't keep saying that I'll pull more transistors in bulk CMOS at least. Okay. So one problem that we then see in all this, right, is that we see that if we increase, if basically our Z naught, let's say we'll call it Z naught divided by uh, RL opt, right, if this ratio increases, the efficiency of my matching network decreases, right, and I can think that my overall efficiency is actually my drain efficiency times my matching network efficiency, right. And if I want to capture uh, the impact of the PAE, then I can write something like this, right. So I can see that in order to basically get a good PAE then, right, I need to make sure that I pick some topology that's giving me good drain efficiency. Let's say I pick class AB or class B. Then I need to make sure that I design a low loss matching network, which becomes challenging when I try to do high output power because my RL opt is low. And I also want to make sure that I design for high gain, right? So one approach at millimeter wave, and I mean it works at RF as well, but it's been employed in millimeter wave, is this concept of stacking, right? So there is a paper by Dabad et al. In TMTT 2013. I wouldn't call it the first paper that does stacking. Stacking has been going on in 3.5s for a long time, but it works through some of the design equations and has some implementations in SOI, right? What is the general idea? The idea is that let's say that I have this transistor over here, right? This transistor wants to see some voltage at the drain, let's call it ZD1, which I'll call R opt, right? What I'll do is I'll put another transistor on top of it, right? And this transistor now at its drain, right, it wants to see 2R opt, right? Because this becomes a series combination of this. So unlike cascode though, I don't AC ground this node, right? I apply some capacitance over here, right? So this is of course my input node, right? And over here, let's say that I have a, right? I bias this node as well, and I have a capacitance here C2, right? And similarly, I can stack one more. Let's just stack one more over here, right? And now basically ZD3 that I need to see is 3R opt, right? And I'll basically have a right. So what I've effectively done is it's like a series combining approach where I am basically noting that I can the optimal impedance that needs to be presented keeps increasing, right? And let's say that here I have some chode / network that basically gives my VDD, right? Now this VDD can be a lot higher because that voltage is getting dropped across 3 devices in the stack, right? So if I basically have a situation where let's say that the VDD just scales with the number of devices in the stack, just as an example, right? In this case, I would have gotten VDD squared divided by 2R opt, right? In this case, the voltage is scaling to twice. So this is 2 VDD squared, but the resistance is also doubling, right? So I'll basically get, let me call this Px, this will be 2 Px, right? And similarly, I can basically see that I'll linearly increase the output power because my BDD is scaling up linearly, right? But as my BDD is scaling up linearly, my voltage swings on this node are also scaling up, right? So I am exposed to the drain body breakdown possibly, right? But if you are operating in SOI devices, that breakdown voltage is very high because there is no drain bulk diode. So in a fully depleted SOI process, if this is the source, this is the drain, right below this, there is the buried oxide, right, or the BOTS layer, right? So I don't have that diode. So basically I can tolerate oxide breakdown, which is of the order of several volts, right? So I can keep stacking this up in order to increase power. And what is very nice is that now at this point, right, effectively since looking up is 3 opt, I'm just redrawing it and saying that this load over here, whatever is my load, should present 3 R opt instead of R opt, right? So the transformation ratio is reduced. So I can get higher output power, get wider bandwidth operation, right? Another option, of course, that I have is I decide that I am going to increase the width of my devices also, right? So basically, I'm going to keep the R opt the same, okay? So I'm going to scale my devices because I'm stacking, right? This is the other way of scaling it, where I scale my devices so that this is now R opt over 3, this wants to see, right? Because I've increased the width of my device. This becomes 2R opt over 3. This becomes R opt, right? So now if I look at the output power that I'm generating, it is 3 VDD the whole square divided by R opt. So in this particular kind of scaling, I'm increasing my output power by 9x, right? But the challenge here is in order to drop the optimum impedance from R opt to R opt over 3, remember that the intuition was VDD divided by I max is R opt. So if I'm dropping R opt, then I have to increase I. If I have to increase I am basically scaling the width of this device, right? So effectively what would have happened is that I'm scaling the width of this device to 3 times each of these devices what it was, right? And when I do that, there are all of these parasitic capacitances that start showing up, right? And I find that it gives me limited benefit, right? So you can mix and match between this and figure out what the optimum device is. There are papers, and even this paper talks about it, and more recent papers also talk about it, about creating matching or impedance shunt networks here to take out the capacitance, or creating series networks here in between to take out the impact of these parasitic capacitances, right? So all of those approaches exist, right? Now in terms of how to bias these devices, well, if I am at VDD, right, and this node is at VDD, ideally I would like to drop 1/3 of VDD on all of these devices, right? So this VDS should basically swing 1/3 of VDD, similarly the next VDS and the next VDS, so on and so forth, right? So I can come up with a biasing rule that says that if I think of the kth device, right, the gate voltage of the kth device should be K minus 1 over K times VDD, right? That gets you to the drain because that's what the drain voltage is scaled, plus the VGS that you need in order to operate. And what VGS you need to pick here matters in the actual practical design, right? So typically what we do is we try to find out what is the VGS that is needed to support the current when the device is operating at its maximum power at PSAT, right? When the stat is operating at PSAT, you try to find out what that VGS is, and then you put that VGS as in order to bias this voltage, right? So effectively, these voltages in the stat are generated based on that. The lowest voltage is of course generated by what class of operation you effectively want things to be in, right? And the capacitances itself, basically the logic of finding the capacitances is that if you consider one of the transistors in the stack, right? Looking up, you'll see ZDK plus 1, right? And you are over here looking at ZDK, and there is capacitances here, right? Right? So you have a network like this. The papers sort of derive what is the impedance that you see. So the assumption is that, okay, I'm going to get this, I'm going to get ZDK to be K plus 1 R opt, right? So I want this to be the optimal here to be K R opt, right? So I can write an equation to make sure that the real part of the impedance here, assuming that the real part of the impedance looking up is K plus 1 R opt, what do I need to do to make this one K R opt, right? So that ends up depending on CK, and you can come up with a design equation that serves as a good starting point in the design. Right? So this is obviously for the second, third transistor, etc. in the stack, right? So based on these design equations, you can put the capacitors at the gate. So effectively, remember, this is different from the cascade because when this node is swinging, some capacitive divider is here. So this node is swinging as well, right? And you can bias this node based on the VDD distribution, right? So this kind of approach has been shown at millimeter wave to be able to work well to create high output power without the need for large transformation ratios, which are difficult to implement at millimeter wave, right? So class AB stacking, these are all sort of popular choices, and increasingly in research, again because of time we're not going to get into it, but increasingly in research what you start seeing is Doherty amplifiers making an appearance, right? And I'll talk about the motivation for building these kind of amplifiers shortly, right? Yes.
Stacking.
Yes.
Can we keep on stacking, or is there a limitation?
So what you find is that as you stack more and more devices, right, you're basically creating a situation where the parasitates start impacting the design. And remember, as you go from 3 to 4, you aren't doubling, right? You're making the improvement 4 over 3, right? And that basically starts disappearing a little bit as you increase the stack and start seeing parasitates. So typical designs have been at 4 stack or 3 stack. Yeah, between 2 and 4 is generally the sort of number that in practice people have been stacking. The breakdown voltage limit, you can maybe go maybe 5 VDD also works. I think there was a paper at ISSEC several years ago which had 6 stats, but that was a line driver, not a PA, but the same principle basically. So before we discuss the principle of these kind of amplifiers, right? Let's discuss some of the non-idealities that are there in the system, right? So the first thing is AM and AM PM, right? So what basically happens is that if I consider then I'm going to write it as V in and V out, right, instead of P in and P out, but it's the same principle, right. So instead of seeing a linear curve, I'm going to see some saturation, right. So this would have been the ideal curve that I would like to see, right. And so as I basically increasing my amplitude, based on my amplitude of my input signal, my output amplitude is changing. So that's AM to AM modulation. And then I can have this AM to PM, where the same phenomena, which but in phase, which is that I look at the phase of the output, right, and I might start seeing some error in the phase of a few degrees as the Vn increases. What does this do? If I consider my let's say quadrature modulation, we discussed this before, but let's say that the constellation points are over here, right. I mean, we have constellation points in all 4 quadrants, but just considering that one, I would like this phase and this phase to be the same, right, but the amplitudes of these two are different. So the PA might might do this phase here correctly, but then this signal might show up here instead, right. And similarly, the amplitude is different, so this signal might show up here while this signal still shows here, right. So this basically creates an error in my constellation, and remember, that is what noise is also doing. Noise is moving these constellation points around, right. So this effectively impacts my ability to receive the signal and is a similar degradation just like noise in my system, right. And the way that we quantify this is the impact of AM and AM PM is by defining what we call error vector magnitude. Right. So the idea here is that let's consider a single constellation point, right. Let's say this is the ideal constellation point. So this would be the ideal vector that I would want to generate. Let's say this is the spurious point that I'm generating, right. So I'm making an error over here, right. So what I'm trying to find is what is the magnitude of this vector, right. Right, and normalize that to, so the magnitude of the error, right, and or rather I guess we are trying to sum over the normalized error squared. Let's say that this vector length is P1, so this would be P1, right. And I sum this over all such constellation points, and let's say I have n values, and then I take this as 1 over n, right. So this is the root of this is the mean squared error, and then I can take the square root of this to get the root mean squared error to get the EVM. Essentially what this is measuring is what is the RMS of this error, normalized a normalized error. The size of this vector normalized to the size of this vector averaged out, right, RMS averaged. So there is this specification is expressed either in percentage or dB, right, and you can if the dB spec is right. So you can get the EVM specification, and you can see that clearly AM and PM, AM and AM PM are going to cross this kind of error vector magnitude, and the more AM PM I have, the more AM I have, the poorer my EVM is going to be, right. And so this is phenomena 1, right? The second phenomena is that again in this kind of quadrature amplitude modulation, what I find is that if my constellation points, and again I'm only drawing one quadrant here, right? But you can see that if I have constellation points like this, there are several the amplitudes of all these vectors are different, right? So I'm basically having a situation where I might have a peak that is here, and then the average will be the average of all the constellation points that I have, right? So when I'm designing my PA, this basically becomes the P out maths of my PA, right? But so I have to design my PA so that maybe this is the saturated power of the PA, and then the right and then the PA is operating most of the time at a lower power than saturated because it's generating smaller amplitude signals. If I don't do this, then this signal will get what we call clipped, right? Because the PA can't generate this power. So even for this constellation point, it will only generate this length of vector, right? So that becomes a problem. So if you look at the PAPR, this peak to average power ratio, right? For popular constellations, let's say 64 QAM, OFDM, right? What you see is that this ratio can be as high as 11 dB, right? And if you are trying to demodulate this, right, the EVM requirements might be of the order of 8% EVM for 64 QAM, and then if you go to 256 QAM, right, you might be willing to only accept an EVM of 3.5%, right? So then overall it becomes a challenge, because in order to make sure that I'm not creating any error, even if my PSAT is over here, I might be forced to operate in the linear region of my PA, right? And why is that a problem? Well, let's consider what happens to the power added efficiency under back off, right? So remember in the class B PA, right, what we saw was that I fundamental was IRF divided by 2, IDC was IRF divided by pi, right? And then what we saw is that PDC will just be VDD times IRF divided by pi, right? And when we design at maximum current and voltage swing, right? Basically, we put the constraint that I fundamental times RL was VDD, or basically we said that IRF maths, right, is 2 VDD over RL, right? And in this scenario, we saw that our efficiency was 78%, right? But now let's say that I'm operating at 6 dB back off. Okay. At that point, my P out is P out maths divided by 4, right? So this means that my I fundamental, right, is I fundamental in the maths case divided by 2, right, because it's I squared times RL. So my fundamental current must have dropped by a factor of 2, right? This basically then you can see that my IRF that is swinging is IRF maths divided by 2, right? And in this scenario, my IDC is IRF over pi again, right? Or it's basically IRF maths over 2 pi, right? So now, if I think about my DC power consumption, right? It's BDD times IRF over pi was my maximum DC power consumption. Now my DC power consumption has come down, right? It has come down to IRF maths over 2 pi, right? It has come down by a factor of 2, but my P out has come down by a factor of 4, right? So my efficiency basically has come down by a factor of 2, right? So once I start backing off and operating, what I find is that my efficiency becomes very poor. Now, what is true is that it isn't that I'm, if I then think about my efficiency, my PAE or efficiency, right, as a function of P out, right, it might look like this, right? There might be a peak point, right, where at the peak I get the best efficiency, but then when I'm going 6 dB backed off, right, I see that I'm already down 2x in a class B, for example. Now, given my constellation, I am traversing this curve, right? Sometimes I'm generating this P out, sometimes I'm generating this P out, so I'm moving up and down this curve, right? So then I can get a concept of average efficiency in my system. But clearly that average efficiency is going to be much less than my peak efficiency if my average power is going to be much less than my peak power, right? So operating at back off becomes a real problem, right? And if all you're doing is designing class A, class AB, class B designs, the only thing that you can do is make different choices of the load impedance in order to accept some clipping, right? Maybe you don't back off as much as the PAPR. The PAPR is 11 dB, you back off only 7 dB and you accept the error because overall your EBM is okay, something like that, right? Or you can come up with architectures that keep this constant somehow, right? That's basically the idea. So again, so effectively there are two ways to do it, right? One, scale supply with output power, right? If I could scale the supply with output power, then my efficiency always would be good because I'd always be operating at a full VDD swing, right? Which is what I want to get. Or I scale resistance with RL with output power, right? And we call this load modulation. We call this supply modulation, right? And in the low gigahertz frequencies, this is done in order to get good efficiency, right? And at millimeter wave, this is now, people are publishing Doherty amplifiers. So supply modulation at millimeter wave is particularly challenging because the supply needs to respond at the rate at which your amplitude is changing, which can be quite high because these are wideband modulations. That's why we went to millimeter wave. So building a wideband supply modulator is quite hard to do. However, trying to do load modulation using different techniques, with Doherty being the most popular technique, is being explored. The idea behind Doherty is quite conceptually simple, but implementation wise it can be done different ways. I'm just drawing a Doherty with what is called an isolating combiner, but you can think about it as two PAs, right? Let's say that there is one PA that is biased in class B, right? And this PA is providing the output power for as long as there is this P out, right, and it has reached its maximum, and then if I need even more P out, then this PA turns on, and let's say that this PA is in class C, right? So we call this the peaking amplifier. So when the input signal swing goes really high, then this transistor, which is in class C, turns on, right? And then it starts adding some power. So then the overall power increases, right? So since the class C amplifier is turning on for a short duration of the cycle, which is what class C does, it's quite efficient. And the class B PA, it is operating close to its peak output power, so it is efficient. So that's an isolating combiner. There are ways to build Doherty with non-isolating combiners with impedance inverters. It's beyond the scope of what we can talk about here, but there are papers and implementations now that are doing that and getting good efficiency. So just to give you a sense of where things are, right? So what you can see over here is 20 to 50 gigahertz PAs, a survey that was done in this paper, right? And if I look at the peak PAE, right, at saturated power, you can see the PAEs are in the 35 to 40% range for these designs, up to about the 22, 23 dBm, right? And then beyond that, the efficiency starts falling, because this over here is sort of the power that you are getting from a single PA, right? And then over here, we are power combining multiple PAs together, right? So then in our efficiency term, there is a eta drain efficiency that we had, right? Then maybe some transforming network efficiency, right? Then 1 minus 1 over G, and now you might have a combining network efficiency, right? So this basically leads to lower efficiency as I try to get even higher and higher output power. But you can also see the significant difference once I look at average efficiency when I am applying an actual modulated signal, because my average output power is lower than my PSAT because I have to back off, and when I back off, my average efficiency drops from the 45% range to the 20% range, right? So this is something that is I'd say a pretty significant research challenge now, where we are trying to all build systems that achieve closer to peak PAE under back-off conditions. Yeah. So just to go through a couple of design examples, right? This is a 28 gigahertz PA in 40 nanometer CMOS, right? And you'll recognize hopefully now some of the matching networks, right? They have this wideband matching networks from input to output. You can see the device scaling as you go from stage 1 to stage 3. You basically have some unit cell devices here, but the driver is 4x and the PA is 8x of the unit cells, right? So this is typically a very conventional way of scaling, where your driver is about half the PA, right? So you're counting on being able to have sufficient gain. If you have about 10 dB gain in the PA, this sort of split works very reasonably, right? And if you're operating with about 10 dB gain in the PA, your Fmax should be about 3x your operating frequency, right? So these numbers just all sort of tie together as you pick your technology. So in terms of a design approach, right, the general idea that they do is they take a unit cell, right, and they are neutralizing it as we have seen in order to increase Fmax, right, and improve the isolation and stability, right. So you neutralize a unit cell, and then we take this unit cell and we build the PA with that. Now even it depends upon particular design approaches, but the general idea is usually to take a unit transistor, right. So you take a unit transistor, do all the layouts, everything on it, do an extraction so that there is an extracted model for this unit cell transistor, right. And then we do load pulls with different number of these transistors in parallel, right. And that gives us an optimum load, and we can decide, okay, and an optimum power, and we can decide, okay, we need n such parallel transistors. Now, of course, we have not considered all that would take to wire these transistors together, right. We have not considered those wiring parasitics. So then there's another round of iteration where we start wiring these devices together and then do another load pull set in order to see whether we are still in the right output power range, right. And these load pulls can be done across V bias, right, in order to find out which is the right V bias to get a certain EVM or to get a certain P out PAE, right. And the process does involve iteration at every step where a reasonable design has been obtained to make the layouts more realistic, because at millimeter wave layouts matter. But overall, in this paper, their observation was that if they biased it a little bit below threshold, right, I think it was like 100 millivolts to 150 millivolts below threshold, it was a good trade-off point between output power and efficiency, right. So they use but if you still want to get a lot of output power when you're biasing so low, you need to array a number of devices together, right. So there are parasitics associated with that. But even after that, if I am operating with my V bias below threshold, what happens is that my AM to PM really is increased, because my transistor capacitances are going through a lot of nonlinearity in the input signal swing. So then in an earlier generation of their design, what they do is they put a degeneration inductor here, right. Sorry, not in the common mode, but in the differential mode, right. So they have a degeneration inductor over here, and when you put a degeneration inductor, you can show that the AM PM is improved, right. But when I put the degeneration inductor, I'm also dropping gain, right. So now so we apply the L degen, right. So AM PM comes down, but gain is decreased, right. And I have to live with that trade-off, right. And one of the observations that they've had, and other publications have also observed this, is that building a wideband interstage matching load helps, because shown here is they're taking that dual resonance load and deciding on the delta F between the resonant frequencies, right, and looking at the impact of picking delta F on the AM PM. And what they see is that if they separate the resonance frequencies, the rate of change of phase with frequency is reduced, and so it is less sensitive to changes in Cin. That's the basic argument that is made, right. But overall then this analysis says, okay, that the resonant load should in the transformation should have a certain delta F, right, that basically gives me a low AM to PM. And then given all this information, I then put this all into my design and then do a final set of load pulls in order to get my overall design with layout. And we can see hopefully by now the sort of layout structures that we are familiar with in terms of interstage matching transformers, neutralization, right? And what we see is that they have PAE at a point where they are 5 dB backed off. The PAE is about 15% across a pretty wide bandwidth, right? And this is for a PA that is about a 15 dBm, 16 dBm. So it's about something like a 40 milliwatt PA. Right, so this is more a handset PA rather than a base station PA, but the design techniques are of course very similar. People are doing dual drive PAs now, where basically instead of just driving the gate, you drive the gate and the source. So I think that is basically what you're implying, to increase the swing at the input twice, GM twice. So basically GM boosting kind of efforts. So yes, there are PAs that are doing that. Yeah. At millimeter wave, there is a paper. I'm forgetting the name of the person. So Georgia Tech had a paper where they were doing gate source drives of PAs. Yeah. This is a good question. So yeah, it's a good question. So when you do class B PAs, you see that happen, right? So particularly if you cascade drivers and PAs and multi-stages together, you get this phenomena where your gain goes up and then comes down like this, right? So this is gain across P in or P out, right? Yeah. So then what you basically start seeing is that your OP 1 dB, let's say that this is P out, right? So this is supposed to be my OP 1 dB. So let's say that this is 1 dB less, right? So should I be looking at really small signal, or should I be looking from here? Because so the challenge is that if I have an array in which I'm distributing signals and I have multiple PAs, then I have the same signal going to all the PAs, right? It's splitting and going. Let's say this is my signal divider, right? So then the challenge is that each of these PAs is different, but I only have one common port. So if I do a pre-distortion here, I may not be correcting for all the PAs, because each of the PA has a slightly different characteristic. So on single PAs, 100%, right, you do pre-distortion, but on arrays, the problem is that you don't have access to it. So this is one of the sort of hidden benefits of if you build a full MIMO array, because then you can do pre-distortion on each PA level, because each of the streams is different. But all that takes power to do. But this is again array level pre-distortion is what this is called. So Forts have tried doing it, right? It's at the margin it helps because there are some common nonlinearities, so it does help. But the challenge is that when you have an array like this, each of the PAs is actually sees a slightly different load depending upon its position in the array. Particularly the edge PAs see a different load than the center PAs. And if this distortion has to be corrected, the pre-distortion is load specific. So that basically starts causing a problem. So you can do analog pre-distortion and things like that, but trying to do digital pre-distortion or DPD becomes challenging at an array level. Get the PA's AM/PM characteristics and AM/AM characteristics, put that into a simulator that then predicts what the EVM will be, and then they see if that is acceptable. So for every load and every bias condition, they're actually simulating what the EVM, which is the end truth, is, and then finding out which is acceptable, right? So that's obviously a multi-step design process, but that is the kind of thing that has to be done for the PA. We discussed stat PA. So in this paper, they actually did a nice thing where they implemented multiple stat PAs a 2-stat, a 3-stat, a 4-stat, and they're also doing this intermediate node, the intermediate node tuning. You can show that basically you want the voltage and the current on these nodes to be aligned with each other, and so you put these networks in order to improve that alignment. But with this, what you can see over here is the power levels, right? So from 2-stat to 3-stat to 4-stat, power levels are going up roughly by 3 dB, right? And they also see that you can get higher output power without too much of a degradation in efficiency, because I'm able to operate without the need for a very high transformation ratio. Instead, I'm doing stacking. And this was another the paper that, we discussed this paper in the context of wideband matching networks, but they also had the same observation that if they do wideband matching, they're able to reduce the AM/PM that they see. The other thing that they do in this PA is the equivalent of analog predistortion, where they are adding a PMOS varactor, right, at the input, so that it is basically, in addition to the neutralization which is taking out the CGD, any C in nonlinearity is balanced out. So this over here shows without the PMOS varactor what the C in looks as a function of V in, and this looks as what C in looks as a function of V in with the PMOS varactor, right? So if you apply the right control voltage, you can make basically the C in look pretty constant across all input voltages, right? And this basically reduces AM/PM as well. And they are able to demonstrate a really wideband PA, right? It's nice work with very low AM to PM across the entire tuning range. Right, so I think this is a logical point to stop, because we'll stop with PAs now and do doublers very quickly and then move to LNAs before the end. So of course you have to make sure that the PA is small signal stable, right? And look at it across all frequencies, not just the band of interest, because very typically the PA can go unstable in low frequencies when you're designing for millimeter wave. That conventionally happens. The challenge is that the PA is usually operating in large signal, so you see small signal stability, but you don't see large signal stability. So you can try things like excite the PA with impulse responses that are large and see transient simulations if the output of the PA dies down. So those kind of simulations are sometimes helpful to tease out common mode oscillations or oscillations that are occurring in large signal impedance modulation conditions. So you provide basically, you can think of an impulse as a very wideband input, and so you are providing input, a large input across a range of frequencies. So if there is a oscillation mode that can occur, the PA can latch on to that, right? There's also good design practice techniques, such as making sure that your supply network is very low Q. So when you bypass the PA supply, so just as an example, we put this L choke, right? And then I put a filter here, right? But this is actually equivalent to a situation where I move this inductor, instead of putting it to ground, I can just put it to VDD, right? The network is still the same. And then I have, maybe I can move this capacitor also. It can be on this side or that side, but putting it on this side helps me absorb the capacitance of the inductor and the capacitance of the device very easily, right? So my network might look like this, right? And then I have a bypass networks to my load, right? These networks look the same, but now the problem is in my VDD, right? So I have to bypass this with large capacitors, but at millimeter wave, these capacitors, their Q might lead to oscillations at low frequencies. So what you typically do is that you have series resistances with these capacitors, right? and you might target something like a Q of 1 or 2 at 1 gigahertz, something like that, a very low Q with this RNC. But now, in order to still get good bypass, you'd make an array of them, right? So the supply basically looks bypassed by an array of detuned capacitors. So you don't want to put a high Q capacitor on the supply node in general. So that's usually the proximate cause of most problems with PAs, right? And neutralization, of course, helps fundamentally to improve reverse isolation across frequency, right? It stabilizes things across frequency. So that's the other step that people usually take in PAs to stabilize. And in practice also, you have to simulate the whole thing, because the other issue is that you get input to output leakage in a PA, and particularly if you have a chain of 3 amplifier stages and together they have 30 dB gain, then you're talking about a system that needs 30 dB isolation on the reverse side or more. So you need to make sure that you're putting that entire network into the simulator, not just the stage that you're designing.